Alright, in this video tutorial, we'll be learning about compensation and subtraction. And once again, we're really connecting to those properties, place value, and inverse relationships. And you'll once again see the power of understanding the quantities that you're working with. So let's define compensation once again. Compensation is a technique we use all the time in math without really thinking about it. It's when we convert a problem to a more manageable one in order to calculate the answer more easily. All right, so before we move into a few subtraction problems, I want to give you an example of what I do with students in the classroom. This is to get them to understand the constant distance between 2 points on a number line. But what I start doing is I stand over by a circular table, so here I am, and I ask them to count how many steps it takes me to go from the circular table over to the star student area where I have star student posters. So I step and they count 1, 2, 3, 4, 5. And I ask them, how many steps did it take me to go from the circular table over to the star student chart? And they'll say 5, okay? So then, very dramatically, I say, now, okay, I'm going to start from the star chart, and I'm going to go back over to the table. Count to see how many steps it's going to take. 1, 2, 3, 4, 5, okay? Not very equal steps there, but just stick with me here. So, either way, how many steps is it? 5. Well, what do you know? It was the same distance. It was a constant distance or difference between the circle table and the star. Okay? So, do some examples like that where students are really having to think about the distance stays the same whether I start here, over at my table, or here. Okay? It's a big understanding for them to recognize, all right? So to compensate means to make a problem easier, okay? So let's think about 9 minus 4 and use a compensation strategy. So here you can see the original problem. Well, I like combinations of 10, so when I see 9 minus 4, I think about it as 10 minus 4 instead. And I think 10 minus 4, I know 4 and 6 equals 10. However, what I've done here is I've added 1, right? I've started with 1 more. So if I start with 1 more in this original problem, then what I need to make sure and do is actually subtract 1 more, right? So that would be an answer or a difference of 5. So if we look at our model here, if we would look at 9 minus 4, and if we were to take away 4, that equals 5. Okay? However, if we add an extra 1 and start with 10, then we need to take an extra 1 away because we just can't start with an extra. So here you can see we've zeroed that out. All right? Another way to think about that would be instead of 9 minus 4, we could just go ahead and think of it, let me use another color here, as 10 minus 5. Now what's happened here? Well, we added 1 to the minuend and we've added 1 to the subtrahend. So we've started with 10, and so if we're going to add 1 more on, we also need to subtract an extra, which is really what we did as well in the previous example. So that would equal 5. Okay? So once again, you can see here in this visual, if we started with an extra, or we started with 10 instead of 9, then instead of subtracting just 4, we're going to subtract 1 more. We're going to subtract that extra, which would be 5. And here you can see in this number line model, in blue we have the difference between 9 and 4, and we have the difference between 10 and 5. And in both cases, we can see that there are 5 increments
between both. So they are the same. That distance or difference is the same. Keep in mind, we could just tell students, you always add one more to the minuend and to the subtrahend and subtract. However, this isn't making sense of the math. So we need to be sure that they can justify and show models as to why this is working so that they know when and what to apply as they're adding, or in this case, they're subtracting. They're using compensation with reasoning and sense making. All right, so another simple example would be just 19 minus 14. Now keep in mind, we start with these simpler problems so that students can kind of mathematically make sense of them. So we could go ahead and think about this as 20 minus 14. And because kids are good at their combinations of 10, they would know that that is 4 and 6 is 10 plus 10 more, perhaps. Okay? So, but because they started once with one more, they need to subtract that extra one away. So that would be 5. Now, it's so important that you have kids with these simpler problems. Prove it with a picture. Show both of these equations on a number line and why are they the same difference. Okay? Here we can see we started with 20 and we actually subtracted 14 and we subtracted 1. So really what we're doing is we're taking 20 minus 15. Okay, so whether we think about it as, adding 1 to that minuend and subtracting that original number, subtracting an extra, or simply starting with 20 and subtracting 15 to get 5. Either way works. So what if we had 50 minus 28? Okay, so if we look at this compensation on a number line with subtraction, we could think about this as 50. I'm going to think about it as minus 30, but you know what? That would be 20 because that's really easy for me, but then I need to give 2 back because I subtracted 30 instead of just 28. So that would actually equal 22. Okay, so you see how the tool of an open number line can be a helpful visual for us to use. All right, let's try another one. I can think about that as 100 minus 90, I know is 10. But I actually subtracted 4 extra, so I need to think about adding that 4 back in to get 14. Okay, so what did I do here? I actually added 4 here, but then I have to make sure that means I subtracted 4 too many, so I need to give that 4 back. Okay, how would that look on a number line? 100 minus 90, oops, just kidding, that was too much. I need to actually give 4 back. So 10 plus 4 is 14. Okay? You can even see that my 86 is right here when we think about positive and negative numbers. Okay? So I subtracted 90, but then I added 4 back. So my answer is 14. Compensation becomes really powerful as we think about, have you ever seen students have problems like this? And more often than not, because of they're using that traditional algorithm, it gets to be very messy because they cross out and regroup several times over. So compensation works beautifully so that we don't have to think about regrouping and that type of thing. So I could go ahead and I'm going to go ahead and think about this as minus 1. So I know that's 9,999 minus 7,000. I'm going to subtract 1 from here, 8,401. So now it'll be a lot easier for me to go ahead and do that subtraction. 2,158. Okay, so what did I do here? I started with 1 less, so I took away 1 less. Okay, is it okay to do that? Talk about that, show that. Go back to a simple example of, is 10
minus 9 the same as 9 minus 8? Is the difference the same? Really thinking about the distance or the difference between those two numbers, that constant distance, okay, as we modeled in the example of the circle table and the star, okay? All right, so here's another great example to help your students understand the difference. So I just give this some dramatic story. I have a student come up to the board and do the recording of the numbers for us, and we have this conversation about why does it always stay the same? What do you notice about the number patterns? So Christy and her sister Jan share the same birthday on December 8th. So Christy, when she was 3 years old, Jan turned 1, okay? So Christy turned 3 and Jan turned 1. So what was their difference in age? They were different in age by 2 years. Every stinking year, Jan was really hoping she could catch up to her sister. I mean, they shared the same birthday. So every year she was hoping maybe she would catch up. But the next year, Christy turned 4 and Jan turned 2. How much older was Christy than Jan still? 2 years, okay? The next year she thought maybe when I turn 3 and Christy turned 5, their difference in age was still 2. And it continued to happen in this way. Is Jan ever going to catch up to Christy's age? Nope. Tell me what's happening in these number patterns. Now, we don't only want students to look across and see that the difference is 2 or 1 down in the pattern, but what if we look at when Christy was 3 and Christy was 6? What do you notice? What's happening to our numbers? And what you want students to recognize is, and have the conversation of, well, there's a difference of we're adding 3, and then we're adding 3 onto Jan's age. Does the difference still stay the same? And why is that? Now, you can show that on a number line, okay, where the number line you're actually moving the same distance. So on that number line, Christy has moved ahead 3 and Jan has moved ahead 3. So they can see that the distance between 1 and 3 is the same as the distance between 4 and 6. It's a distance of 2. All right?
All right, so another thing we can do with students is we can provide them with a yardstick or a meter stick, and that will serve as a number line, and a piece of yarn or string. And I oftentimes give the scenario of this is a road, an ant road, so it's kind of small and short, and that kind of helps them with the scenario. So almost like it's a log that gets shifted is kind of how we think about it. So here you can see on the number line that the ending point is at 4, the starting point is at 1, and what is the difference or the distance between 1 and 4? So we can go ahead and see that it's 1, 2, 3. Okay, so the difference between those 2 points is 3. All right, so here you can see that the log or the ant road has shifted. So we can see that the ending point is at 5, the starting point is at 2. What is the difference or the distance between the starting and ending points? 1, 2, 3. And one more example. 4 and 7. So here we have 7, the ending point, 4 is the starting point, and the distance or difference between those 2 points is still 3. Now, what's really powerful here is you will see an additional resource that we've provided that would help your students engage in this activity. in small groups or partners in which they are physically moving the string and recording the points. And then the real power is when you have the conversation and help them see the pattern and the structure of the difference between those points. So what's really interesting is students will start to notice, because you've asked them, is, take a look at the relationship between the red equation and the green equation. What's happening? What do you notice? What's that relationship? Oh, we've actually increased the ending point by 3 and the starting point by 3. Oh, so that road has shifted. So if the starting point shifts forward 3 places, then the back of that road is going to shift forward 3 places as well. But once again, you could talk them to death, but unless they physically can see and record and start to discuss those patterns and why it's happening, that's where the real power will be. Otherwise, they will begin to wonder, when do I add one? When do I subtract one? So it's critical that they're reasoning and making sense of it.
All right, so let's take a look at a few student examples involving subtraction and compensation. This was a number talk example that was done on chart paper, and the problem was 99 minus 17. So this particular student thought of it as subtracting 9 because that was easy for him. So he took 99 minus 9 to get 90 and then minus 10. Well, he said, I subtracted 19 and I should only subtract 17, so I need to add 2 back to get an answer of 82. Let's take a look at a couple other examples. Here you can see the problem with 600 minus 197. And in this case, 3 was added to both numbers, the subtrahend and the minuend. So in this case, the student thought of it as 603 minus 200. And it was really easy at this point because they're good at subtracting 200 from 603. And here you can see in this example, subtracting across zeros is very difficult. So in this particular case, by subtracting 1, the student really made the problem much easier. So now instead of having 8,000 minus 1,492, we have 7,999 minus 1,491. And then that process of subtracting was much easier. All right, so hopefully you have an idea of some of the ways that kids may represent their method of compensating in subtraction. And I really do hope you noticed that there was very much an understanding of that sense of quantity and how they can be flexible with manipulating those numbers.